Hey everyone, this is going to be a walkthrough from start to finish on creating a plugin for Guitar Hero 3 using GH3+. In this tutorial, I'm going to create a fully functional mirror mode plugin for Guitar Hero 3. You will at minimum require a copy of Visual Studio along with the GH3+ solution in order to compile the plugin. I'm using Visual Studio 2015, so you may have to fiddle with the settings if you're using another version of Visual Studio. You should have the latest version of GH3+ installed already, otherwise you're going to have a hard time testing your plugin. You really should have a copy of IDA, the interactive disassembler. Along with this, you should download a copy of my IDA database for Guitar Hero 3, as I've already mapped a large amount of the binary. I will not be able to help you if you are using another disassembler. You should be somewhat knowledgeable in C, C++, and x86 assembly. If you are not, most of this tutorial will likely be way over your head, although you could probably manage if you have some knowledge in programming and a willingness to learn more. We will also be using Nanook's Queen Bee. I'm sorry if I got that pronunciation wrong. We'll be using Nanook's Queen Bee in this tutorial for some preliminary investigation in Guitar Hero 3's pack files. You may want to have a copy of Cheat Engine, as IDA is very slow when scanning a process's memory. Cheat Engine is also useful for watching values change in real time. However, I will not be using Cheat Engine in this tutorial. I have a link for everything in the description. Visual Studio and IDA are both very expensive software. If you are not a developer with thousands of dollars of disposable income, you should look into acquiring these via other means. There's a couple steps to making a plugin. The first step we're going to be doing is forming a theory about how Guitar Hero 3 handles the functionality we're going to be modifying. We're going to be modifying the game's loading of note tracks. Specifically, we're going to swap blue and red, as well as green and orange, in order to mirror the note chart. But how does the game store the note tracks internally? It probably doesn't use feedbacks.chart format. So, before we progress any further, we should get some info on this, so we can recognize any code dealing with note charts. Since we're all intimately familiar with Through the Fire and Flames, we'll gather some information with that. If we look in our Guitar Hero 3 data folder, we'll find that there's 3 Through the Fire and Flames files. Through Fire and Flames.fsb.zen lives in data music, and it's 40.8 megabytes. A Google search reveals that the extension FSB stands for Fmod Sound Bank, so this almost certainly contains the song's audio tracks. The second file is through fireandflames.dat.zen. It also lives in data music, but it only is 148 bytes. Considering Through the Fire and Flames has over 10,000 notes between all of its note tracks, we can assume that even with compression, that it probably isn't this file. The last file is through fireandflames_song.pack.zen, which lives in data songs. This is a pack file which can be opened in Queen Bee. With a short amount of time poking around, we come across 4 long arrays of integers labeled with easy, medium, hard, and expert, corresponding to the game's difficulties. There is an obvious pattern of groups of 3 in this array. You always have a big number followed by 2 small numbers, with the big number always increasing. This pattern repeats throughout the entire array. A reasonable amount of intuition will lead you to the following information. Number 1. Each note in the song's difficulty track is a set of 3 integers. We can confirm this by totaling up the amount of integers in the array and dividing it by 3, which gives us the exact amount of notes in Through the Fire and Flames expert chart. Number 2. The first number is the note's offset in the song in milliseconds. We can confirm this with a stopwatch, and we'll see that the first note in Through the Fire and Flames happens at exactly 2,414 milliseconds. Number 3. The second number is the note's length in milliseconds. Standard Guitar Hero 3 charts tend to have values greater than 1 for this, although custom charts tend to have 1 for any non-sustained notes. Number 4. The third number is the note's combination of frets. The standard Guitar Hero 3 fret bit mask is composed of 6 bits. Bits 0 through 4 are the standard frets, being green, red, yellow, blue, and orange. Bit 5 is the hammer-on pull-off flip. If this is set, the hammer-on pull-off status of the note will be reversed. This is how you force strums or hammer-ons. The other 26 bits of the bit mask are unused, unless you include my tapping hack, in which case bit 6 is the tapping flag. Alright, that's a fair amount to go off of then. So I'll move on to the next step, which is finding the code responsible so we can make our changes. Since we want to create mirrored notes, we need to find the code that creates the notes that the player can hit. There are two main ways to go about this, with some bleeding between the two. The first is by setting some sort of signaling value and then scanning for it. I'll explain this in some more detail later. This is a pretty good approach if you're going in blind and want results fast. The second is by purely analyzing the code. If you have prior work done, you can look for a key, variable name, function name, or some other identifier related to the functionality you're looking for, or if you don't, disassemble and analyze areas related to what you're looking for. Since I have mapped a very large amount of the Guitar Hero 3 executable already, you should probably start here. So the first method, analyzing. Doing this purely through analyzing code can be really slow if you don't have some sort of lead already. If I was doing this purely through analyzing code, I would probably look for some keys that are related to the functionality I'm looking for. Quick aside, in Guitar Hero 3, keys or key keys are CFC32 hashes of strings that Guitar Hero 3 uses to quickly access data. A computer can compare and operate on hashes much faster than full strings. So from my existing knowledge, I know that Guitar Hero 3 has battle mode. And in battle mode, there's an attack called double notes, which alters the loading of notes in Guitar Hero 3. If I can find where the double notes power-up acts, I can probably find where the code responsible for placing notes is. I will admit that reaching this conclusion is somewhat of a long shot, but roll with me here. The QB key for double notes is 6A, 8C, D6, E2. The function this is used by is sub41CF70, which is of course located at 41CF70, which is also the function we need. I renamed this function to add note to input array for ease of readability. And now we'll do this with the other method, debugging. Usually I'll resort to debugging when I get tired of analysis or hit a wall. With this method, we're going to essentially be using what is a trick to find out what code is accessing the note chart. So first, we'll open Queen Bee to one of our custom songs. I'm using Amalgamation. The song Amalgamation starts off with orange, 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 red, orange. We're going to change the fifth note's fret mask to be a magic number instead of orange. Our value will be the hex value, which basically it looks like diseased. D1, 5E, A5, ED. Now we're going to start up GH3 and attach IDA as our debugger. You could potentially use Cheat Engine or some other debugger here if you prefer. Once we load Amalgamation, we're going to pause the game and scan the memory for our signaling value. When our signaling value is found, we find ourselves in the expert note track of the song. Our signaling value, disease, represents the frets portion of the fifth note. The value before it, 1, represents the note's length, 1 millisecond. The value before that is the note's offset, which is 7,333 milliseconds. We will now breakpoint the fret mask of the fifth note in order to find out what code uses it. So with that, we will resume execution and watch what happens. As the fifth note is about to load, our breakpoint is hit, and we find ourselves in the same routine as the one we were in the pure analysis method. For fun, if we let ourselves continue, we will see that there is a weird hammer-on pull-off chord where the orange note used to be. If you remember the fret mask information from earlier in the video, you might remember that we showed 7 bits, one for green, red, yellow, blue, orange, hammer and pull off flip, and tapping. In reality, though, the fret mask has 32 bits. If we take our signaling value diseased and convert it to binary, we can easily see which bits of the fret bit mask are set. As we can see, green, yellow, blue, and the hammer on pull-off flag are set. In addition, the tapping flag and a bunch of other values are also set, but since Guitar Hero 3 is not using those, they have no effect. Alright, so regardless of what method we used, we found the code, and now we need to figure out how it works. Reversing a function from scratch can be a long and painful process. After you get started on it, though, your revelations about the code will avalanche, making the rest of it easier to understand as you go along. For example, if I find a variable that corresponds to the note array of the song, that will reveal to me which variables refer to note times, note lengths, and note frets, which in turn gives us some more information. So if I see two sets of note times being compared, I can reason that the result is probably being used to calculate whether the note should be a hammer-on, for example, and so on and so forth. So let's go over what the function does in order to create a note. I'm going to ignore the beginning since that's all mostly set up and it isn't worth the time to go over. Here, the game starts calculating the length of each sustain in the note. For whatever reason, for notes placed on the highway, Guitar Hero 3 keeps track of the length of each fret separately, even though there's no way to create a chord with different sustain lengths on individual frets. It even does this for the hammer-on pull-off flip flag, even though it is quickly discarded afterwards. After calculating the note's frets and sustain length, it goes on to determine whether the note should be a hammer-on. It does this by comparing the time difference of the current note in the previous note against the hammer-on pull-off threshold, determining whether the current note is a chord, determining if the current note has a different set of frets than the previous one, and determining if the hammer-on flip flag is set. After this, the game determines if the double notes attack is activated, and if it is, it forces the hammer-on flag to be 0. It then goes through a forest of logic which turns single notes into 2-note chords, and 2-note chords into 3-note chords. The game then determines the time of the next note. If this is the last note, the next note is set to be at 2 hours. Getting the time of the next note is presumably for tipping off the engine when it's going to need to place another note on the highway. Finally, we create the note. Now that we finished our analysis on the code, it's time to start our hack. In the create note function, we're going to swap the red and blue parameters as well as the green and orange parameters. This will create a mirrored note. To do this, we're going to take over the creation of the parameter list for the create note call. The parameter list for the call starts getting set up at 41D and 41B. This is where we'll take control. After we set up the parameter list, we'll return control at 41D 449, where create note will get called. At this point, I'm going to create a project for the plugin in Visual Studio. In the GH3 Plus solution, we're going to add a new project to the plugins folder. We'll use the template for a Guitar Hero 3 Plus plugin project, and we will name the project Mirror Mode. In mirrormode.cpp, we're going to create a constant for where we're detouring Guitar Hero 3's execution. Then, we're going to create the function where we set up the parameter list for creating the note. It is important that you mark this as a naked function. When you mark a function as naked, you are telling Visual Studio that you will manage the stack frame by hand, and that if anything goes wrong, you will take the blame for it. If the function isn't marked naked, Visual Studio will emit code at the beginning and end of the function to manage the stack frame. When Guitar Hero 3 is routed into this function, it will wreak havoc and the game will crash. And then we have the apply hack function. Apply hack will be called when the plugin DLL is loaded by the Guitar Hero 3 Plus core. This is a rather crude solution, but it's how it works for now. In the body of apply hack, we will use our global instance of the Guitar Hero 3 Plus patcher class to write a jump from the detour location we marked earlier to our function that will set up create notes parameter list. The Patrick class methods will use Windows to bypass memory protection and write directly to Guitar Hero 3's read-only memory. It'll keep track of all the data it overwrites so that when it's destroyed, it can revert all of its changes. In addition, there's protections in the Patrick class to make sure it's not overwriting a patch written by another plugin. If another plugin happened to have patched our detours location before us, our attempt to write a jump there would fail. If your Patrick class is writing to multiple locations, you should make sure to remove them if any of your writes fail, otherwise you'll have a partially loaded plugin. Since our patcher instance is static, our jump will persist for the remainder of the plugin's lifetime, which as of now is forever. To start off with, we're just going to do exactly what the original code is doing. So exact, in fact, that I'm just going to copy and paste the code from the disassembly listing right into Visual Studio. Now we have a plugin. We're going to compile it and then place it in the Guitar Hero 3 plugin directory to be loaded. Then we'll start Guitar Hero 3. So after picking a song and seeing that it doesn't crash, we have our confirmation that our code is probably alright. And if we go check the debug.txt generated by Guitar Hero 3 Plus, we can see that our plugin was loaded successfully. Now we're going to go about reordering the parameter list so we get some mirrored notes. This is a little tricky because the instructions are laid out in a manner optimized for speed and not readability, but we can still manage. After we finish, we'll compile the plugin and test it again. The first note in Knights of Sidonia is green and red, so we should see a blue and orange here. And we do. So it appears the hack is working. But we're going to just keep watching a little bit longer to see if there's any problems. And there is. Strings of greens, reds, blues, and oranges are becoming hammer-ons and pull-offs instead of normal strums. To understand why this is happening, we're going to head back to the hammer-on calculation in the note creation code. There are 3 conditions for a note to be a hammer-on, excluding the hammer-on flip flag. The first is that the note must be close enough to the previous note. The second is that the note must not be a chord. And the third is that the frets of the note must be different than the frets of the previous note. But that third point isn't true, right? Like, obviously a string of blue notes following each other all have the same fret mask, blue. So what's going on here? The answer becomes a little more obvious when you look at where the fret masks are coming from. The current note's fret mask is retrieved from the track array. This is the array holding the entire note chart, from start to finish. The previous note's fret mask, however, is being retrieved from the input array, or worded another way, the place notes array, the notes you see on the highway. So the game thinks it's placing a red note, since that's what it would be in the real Knights of Sidonia chart, but it's comparing it to a blue note since that's the swap note that's already on the highway. Since these aren't equal, it decides that it should be a hammer-on. Now, there's a couple ways we could fix this, but the approach I'm going to take is by mirroring the function that gets the fret mask of the place notes. We're going to do this by completely re-implementing the function in Visual Studio instead of hacking apart the existing one in Guitar Hero 3. Since we're going to be completely re-implementing the function, and because the original function uses a fast call calling convention, we won't need to use a naked function to set up the stack. First, I'm going to define an enumeration and structure that the function will be using. The first is an enumeration for the fret masks used by notes in the input array, rather than the track array that we looked at earlier. It is actually kind of neat because the values never self-picked for this resemble the held frets when you view it in hexadecimal. The second is a struct called the QB array, which is 12 bytes long and holds a set of flags, an integer to keep track of its size, and a pointer to an array. Now we'll implement the function, which must be a fast call or it will crash when we detour to it. It will essentially be the same as the decompiled pseudocode generated by IDA, but with the green and orange flipped and red and blue flipped. After the function is written, we'll make sure we detour to it in the apply hack function. All that is left to do after this is to compile and test it. And we can see that the fix works. Mirror mode is finished, and this is the end of the tutorial.